In this objective, we're going to be talking about 6.9 Hess's law. So the learning objective states that we should be able to represent a chemical or physical process as a sequence of steps. So first things first, I want to talk about just a few various enthalpy change definitions just to kind of tie everything together at this point. So again, for standard state, for a gas, this is the pure gas at a pressure of exactly 1 atm in 25 degrees Celsius. For a liquid or solid, this will be the pure substance in its most stable form at a pressure of 1 atm. And for a solution, we're talking about concentrations of exactly 1 molar. So let's talk about the other delta H's. So if you ever just see a delta H, we're just talking about an enthalpy change applying to reactions done at constant pressure. So this will be in kilojoules. If you ever see a standard enthalpy change, we're talking about the same thing above, but we'll have the not, indicating standard conditions, okay? Here, this is still going to be in kilojoules. If you ever see delta H reaction or delta H R, this is the standard enthalpy change of a reaction. This is going to be the enthalpy change which occurs when quantities of materials react under standard conditions. This will be in the units kilojoules per mole, okay? And then lastly, we have delta H formation. It could have the not, here we'll put standard. Again, this is the enthalpy change which occurs when 1 mole of the compound is formed from its elements under standard conditions. This will also be in kilojoules per mole. And we know that a delta H formation for an element will be 0. Again, just to tie things together, my advice, always see what the question's looking for. Looking at the units will help you, especially if it's a multiple choice, they'll tell you, oh, it's in kilojoules, or here, if it's some type of one, and they put, I want this in joules per mole. You just kind of have to see what's going on, okay? Right, moving on to Hess's law. So if a reaction will be the sum of 2 or more reactions, the delta H reaction for the overall process will be the sum of all the other delta H reaction values of those reactions. So the principles of Hess's law, we have 3 of them. It's very important. When a reaction is reversed, so instead of going the forwards direction, we're now going in the reverse direction, the backwards. The enthalpy change stays constant in magnitude. So the value itself will not change. The only thing that changes is the mathematical sign. So we will reverse the mathematical sign. So here, if it was endothermic going in the forwards, it will be exothermic going in the reverse. When 2 or more reactions are added to obtain an overall reaction, the individual delta H reaction of each reaction are added to obtain a net enthalpy of the overall reaction. And lastly, if a reaction is multiplied by some factor, then delta H is also multiplied by the same factor. This also goes along with division as well. So here, if you had X making Y, had a delta H of, let's say, 5 kilojoules, okay? And let's say you want to multiply the entire reaction by 2 to get 2 as the coefficient. So it becomes 2x making 2y. Your new delta H now is 10 kilojoules because we had to multiply it all by 2. So however you manipulate the reaction, you need to do the same thing to the delta H. When the products of a reaction are at different temperatures than their surroundings, they exchange energy with the surroundings to reach thermal equilibrium, which we have talked about in previous objectives. Here, thermal energy is transferred from the surroundings to the products of an endothermic reaction. All right, so let's put this all together. This objective is very hard to teach because you kind of just need to be thrown in it and see how the example works, okay? So right here, this is the reaction that we are trying to find a delta H reaction for. Now, the only reason that we would use Hess's law is for reactions that are very hard to manipulate in the lab. So this reaction is taking graphite, carbon, with hydrogen gas to make methane. This is a very, very difficult reaction to actually compute in an actual lab. So here and it's also to the fact that the reaction is very slow. And so here we know, when I say we, I'm talking about chemists, but chemists know there are 3 different reactions, as mentioned below, that can actually help us get a proposed delta H reaction for this if we manipulate the other 3. So how I like to approach this is I like to look at every single species and I try to find them in the equations below. So I'm looking for a carbon with 1 as its coefficient. It's a solid and it needs to be a reactant. So I actually notice right now in equation 1, it is a reactant. It has a coefficient of 1, so I actually don't need to do anything to equation 1. I'm going to leave it exactly how it is. Next, I am looking for a coefficient 2 hydrogen gas as a reactant. Here, I see hydrogen gas as a reactant, but I don't see that coefficient of 2. So I'm actually going to multiply this entire equation 2 by 2 to get us a 2 coefficient for hydrogen. Because I'm manipulating that equation, I'm going to come over to the side here and I'm going to multiply that entire delta H reaction by 2. Next, I am looking for methane, CH4 gas, as a product. Here I see methane in equation 3, but it ends up being a reactant and I really need it as a product. So here I'm going to actually reverse this entire reaction to make these our reactants and these our products. Because I'm reversing, we are going to need to reverse the sign. So I'm going to rewrite all of those equations below how I manipulated them. So here, equation 1 stayed how it was. And I will note, watching your states of matter is very important. Here, because I did not do anything to change equation 1, I will leave it exactly how it is. This one I multiplied by 2. So everything needs to be multiplied by 2. So my delta H2, or the equation 2, changes to negative 571.6 kilojoules per mole. And then equation 3, we are reversing the reaction. So now our products are reactants, and our reactants are products. So delta H3, we are going to keep the actual magnitude of value, but change the sign to positive 890. So, based off the principles we talked about, okay, principle 2 is saying when we add up the total, we should just add up all the delta H's, okay? So, I'm going to end up crossing off things. Kind of think about spectator ions, okay? Here, I see CO2 gas right here. Those will cross off. I see 2 H2O liquid. I will cross those off. And I see 2 oxygen, and I have 2 oxygen right here. So all that I'm left with is that carbon, that graphite, the 2 hydrogen gas, making CH4 gas. And then, based off principle 2, I will add up all those delta H's, negative 74.8 kilojoules per mole. And this matches the one previously. Okay, again, I would definitely advise you to try to circle where you see one of the species that you're looking for, and then think about how you can manipulate it to look like the one we're solving for. All right, I have example 2 for you right here. Why don't you pause the video, try this out yourself, and then press play, and I'll go over the answers. All right, so looking at this one right here, I first looked at the H2O2 and I found it in equation 2. It sadly did not have my coefficient of 2, so I multiplied it all by 2. And also the H2O2 was a product and I need it as a reactant, so I reversed the equation as well. I then found the 2H2O in equation 1 where it was a product, and that's what I needed it as. Coefficient looked great, so I knew I did not need to manipulate equation 1. You will notice with the oxygen, sometimes you're going to see you have a chemical species that's found in every single equation. My advice, if you can figure out the other two species, everything should work out accordingly. I right here was like, you know what, I'm going to put faith that I got the H2O2 and the water all good. The oxygen should fall into place because I have those other two good. Okay, so here you can see I rewrote the equations accordingly. I manipulated the delta H's accordingly as well. I saw right here the hydrogens crossed off, and then the oxygen, I will get rid of all of this, but this had a coefficient of 2, so this only changes to a coefficient of 1 now, okay? And again, that might happen. You just have to be wary of that. And again, writing out everything will help as well. And then based off principle 2, I added up all the delta H's and I got my overall as negative 196 kilojoules per mole. Okay. I also have another one for you. This will be the last you do problem. So why don't you pause the video, try this out yourself, and again, take this very slowly. Okay. All right. Good luck. All right. So I think the biggest thing in this one is being careful about states of matter. I noticed that A was a solid and a gas in this reaction. And then the A2B was a solid, a liquid, and a gas. So you have to be very, very careful. That's why I find it very important to highlight and circle where you see your chemical species. So I found the A solid in the first reaction, multiplied it all by 2. Then I found the B gas. It was exactly where I needed it, did not need to change the reaction. And then in equation 3, I found the A2B solid, okay? Knew I needed to reverse. Now, before you neglect the last equation, there's probably a reason why it was included, to cancel out any of the other species. And so I noticed that right here we had A2B gas. Now down here I see A2B gas as a product, okay? Well, I cannot manipulate this equation because I have exactly where my B, where it needs to be as a reactant. So here I can reverse this reaction to bring A2B, switch places, gas and liquid, and then I can get rid of the liquid because we're reversing this one as well. So here you can see all the way down here, the A gases cross off, the A2B gas cross off, and the A2B liquid cross off. Then after manipulating all of those delta H values to times 2 and reverse, I added up and got negative 52 kilojoules for that entire reaction. Overall, take your time with this. Always circle, cross things out just to verify that you got the overall that you were looking for.